We just crossed 50,000 subscribers. Thank you. To celebrate, we are exploring one of the most important ideas in AI right now. What if today's AI is wasting most of its intelligence? Elon Musk thinks the gap may be far larger than most people realize. GPT-5 is impressive. But in this view, today's AI may still be closer to the Model T than the Ferrari. Not because the machines are weak, but because the intelligence inside them may be spread out inefficiently. Musk has called this problem intelligence density. How much useful intelligence can fit inside a given amount of model size, memory, power, and hardware? His claim is bold. He believes today's AI may be underperforming its potential by roughly 100 times. In this episode of retrieval, 1C Mind Machine Atlas, we are not here to repeat that claim as fact. We are here to understand the idea behind it. Think of two books that take up the same space on a shelf. One is filled with clear explanations, deep connections, and useful ideas. The other repeats itself, wastes pages, and hides the important parts in noise. Both have the same size, but one carries more meaning. Intelligence density asks a similar question about AI. For every gigabyte of model data, how much reasoning, memory, perception, planning, and problem solving do we actually get? A model can be huge and still use its space badly. Another model can be smaller and feel more capable because its internal structure is more efficient. For years, the main story of AI progress was scale. More data, more chips, more parameters, more electricity, and scale really did work. Larger models became better at language, coding, images, tutoring, and many forms of reasoning. But scale has limits. Every extra layer needs memory. Every token costs energy. Every new model asks for bigger data centers and more specialized chips. If AI only improves by getting physically larger, then progress becomes expensive and concentrated. Intelligence density is the counter question. What if the next major jump comes not from making the machine bigger, but from using the same machine better? Hardware is the visible part of AI progress. We can count GPUs, measure power, and build enormous data centers. Software is harder to see. It lives in architectures, training recipes, memory systems, optimizers, retrieval methods, quantization, sparsity, and post-training. But software can change the economics of intelligence. Picture a simple graph. On one side, the cost per unit of intelligence starts high. Then, better design pushes the curve downward. If an algorithm learns the same skill with less compute, then it is almost like the hardware became stronger overnight. Researchers have already measured this effect. In some areas of machine learning, the amount of compute needed to reach a past performance level has fallen dramatically over time. That means better algorithms can multiply hardware instead of merely depending on it. The history of AI is full of these quiet efficiency jumps. Transformers made it easier to learn long-range patterns in language. Better scaling laws helped researchers balance model size and training data. Quantization allowed models to run with fewer bits. Distillation helped smaller models imitate larger ones. Retrieval systems let models consult outside knowledge instead of carrying everything inside their weights. Mixture of experts architectures activate only parts of a model for a task. None of these changes look as dramatic as a new supercomputer, but together they move intelligence from brute force toward design. They increase how much capability can be packed into each byte, watt, and second. When Musk talks about a 10 times improvement per year, the important idea is compounding. A 10 times jump does not only mean a slightly smarter chatbot. It could mean the same task costs 1/10 as much. Imagine a coding assistant that once needed a powerful server, now running smoothly on a laptop. Or a model that once needed a $2,000 GPU suddenly working on a phone. Or a school, clinic, or small business using tools that once belonged only to large companies. After 1 year, the tool feels cheaper and faster. After 2 years, entirely new workflows become possible. After 3 years, the old limits start to feel artificial. But this future is not automatic. Algorithmic progress is uneven. Some breakthroughs arrive suddenly, while others slow down. If intelligence density rises sharply, AI stops feeling like a scarce supercomputer service and starts feeling like a general layer of the world. Tutors become more personal, and every student could someday have a patient guide that costs pennies a day. Research assistants become more persistent. Design tools become more conversational. Robots can carry more useful models on board. Devices at the edge can understand more without sending everything to the cloud. The key change is not that every tool becomes magical. It is that useful intelligence becomes cheaper to place wherever decisions happen. The more intelligence we can fit into smaller systems, the more AI moves from a distant data center into ordinary work, learning, medicine, science, and daily life. So the real question is not only how big can AI become, it is also how much intelligence can we fit into what we already have. Musk's 100 times claim may be optimistic, but the direction is real. Better algorithms can make the same hardware feel more powerful. That is why intelligence density matters. It turns AI progress from a race for bigger machines into a search for better understanding. And if that search continues, the next era of AI may not be defined only by more compute. It may be defined by abundant intelligence. Smaller, cheaper, faster, and woven into the tools we use every day. What do you think? How dense can intelligence still become?